Okay, hello everyone. In our last class, we have been discussed calculation of system of matrix for a thin lens. In detail, we have been discussed, and we found the system of matrix of a thin lens is this one: 1 0 minus 1 by f 1. Here, f is nothing but the focal length of the thin lens. Okay. In general, the system of matrix of thin lens is represented as like this. So these are the location of cardinal points. With the help of this equation, we can find the cardinal points of a thin lens. Okay. In this class, we are going to discuss find the equivalent focal length and cardinal points of two thin lenses separated by a distance and with a numerical upon this topic. Okay. So let us start here. This figure represents two thin lenses having focal length f1 and f2. This is your lens 1 and lens 2 separated by a distance t. And here you can see in this dotted line we can see the two lenses separated by a distance t, and this is your inside this dotted box. Whatever we have, that is nothing but called as your optical system. Here optical system is nothing but two lenses separated by a distance t. Okay, same thing I have been written in the note. You just write down in your note for your exam point of view. Here f1 and f2 are the focal lengths of two lenses. From figure, what we can notice, an incident ray AB, which is starts from A, first refracted through lens L1, at B at this point, then translated from B to C. So this is the translation, B to C. Then refracted through L2 at C. Same thing I have been written over here. Then the ray refracted through L2 lens 2 at C, then transmitted and finally converged at D. So this is the whole dynamics, ray dynamics. Okay, or you can say ray diagram. From figure, it can be noticed that the ray undergoes two refractions, that happens at B. One happens B at B R1, at C R2. Two refractions and one translation. If I am going to consider only for the system of matrix, for the optical system, we have to just exclude the translation, these two translations. So for the optical system, we have three dynamics. The ray undergoes two refractions which are happens at B and C, and one transmission from B to C through the optical system. Okay, so these dynamics at two refractions and one translation are going to be used to find out the system of matrix of this optical system. So for faster refraction, the refraction matrix Rm1 through L1 at B is represented by what? 1 0 minus 1 by f1 1, because this is the thin lens, and in the last class we discussed this is the system of matrix of a thin lens. So for the faster lens having the focal length is your f1, so instead of f we have to write f1 right here, f1. Okay, likewise for the second refraction, this should be second. Okay, mistakenly written. For the second refraction, the refraction matrix Rm2 through L2 at C. First I have to correct it, just wait. For the second refraction, or the here I written the what? The second refraction matrix through L2 at C. Okay, at C represented as 1 0 minus 1 by f2. Here f2 is the focal length of this lens 2 1. Okay, then translation matrix through the translation matrix Tm through the medium in between these two lenses. I just not written over here, through the medium, or you just write this one. No need to write this this one. The translation matrix from B to C, you just write translation matrix from B to C, that's it. the translation matrix from B to C, which happens in between the two lenses, is represented as 1 T01. Here, see, in general, the translation matrix is represented as 1 T by mu 01. Here we consider that in between these two lenses, air medium is there. So if air medium or vacuum, mu will be considered as 1. So the translation matrix here, it is considered as 1 T01. Okay, okay. Now we have to write the system of matrix of this optical system. So here, this is your image information, this is your object information. May you remembered uh, uh, when we discuss the system of matrix in general, if you have been saw that video, if you not saw, you go and watch that video. Okay, here I'm going to show you that that slide. Here I'm going to show you shortly. Here, this one. Here system matrix act as a operator, right? Act as a operator. If we have initial information or object information, then we can found the image information by using the system of matrix. So here, if this is a system of matrix, this is your first refraction, this is your second refraction, and this is the translation. So for this case, for this thick lens, the system of matrix is what? Rm2, second refraction matrix, into translation matrix, into fast refraction matrix. This whole, after multiplication of these three matrices in this way, in this order, we can found the system of matrix of this thick lens. So first second refraction, then translation, then first refraction. Okay, in this order we have to consider. So likewise here, in our case we have to consider first second refraction, then translation, then refraction. Okay, just wait here. That means first we have to write the second refraction matrix, then it will be multiplied with translation, then first refraction. After multiplication, obviously this will be a 2 cross 2 matrix, and this, after multiplication, this will be called as your system matrix of this optical system. Now we have to just substitute these values whatever we have in our previous slide. Here Rm2 value is your 1 0 minus 1 minus 1 by f2 1, Tm is your 1 T 0 1, and Rm1 value is your what? 1 0 minus 1 by f1 0. You just multiply these three matrices and you can found this one, this value. Or just I written these two terms first. Here 1 minus 1 by f1, this term I written first, then minus 1 by f2 plus T by f1 into f2, and these terms written as such. Okay, here this term written first I written 1, then this term written second, 1 minus T by f2. This one is the system matrix. Just remember, this one is the system matrix uh, of this optical system, that is your two lenses separated by a distance. Here this is your equation number 1. In general, system matrix is what? ABCD. That is your system matrix of any optical system in general. Let this is your equation number 2. Now here, before we are going to go our next slide, you just recall any optical system we have and its corresponding system matrix at that time will be accepted if its determinant will be 1. You just consider this matrix. If it will be accepted as system matrix of this optical system, we have to just verify, take the determinant of this matrix, do it by yourself in your rough. You can found the determinant will be 1. That means here this system matrix is true for this optical system. Now we are going to go for our next slide. Here is equation number 1 and 2 I written again here. By comparing 1 and 2, equation number 1 and 2, if I am going to compare, A value is your this one 1 minus T by f1, B is your T, C is your minus 1 by f1 minus 1 by f2 plus T by f1 f2 or f2 f1 or f1 f2, or C, if I'm going to take common minus from all these three terms, then we can found 1 by f1 plus 1 by f2 minus T by f2 f1 or f1 f2. Okay, and D value is your this one 1 minus T by f2. Okay, it is well known that the equivalent focal length, which is FEQE, U represented as like this, of combination of two thin lenses separated by a distance t, which is placed in a medium having refractive index mu. Follow this figure: two thin lenses separated by a distance t, and this whole system, optical system, placed in a medium having refractive index mu. If it is so, then equivalent focal length is nothing but equal to f1 f2 by f1 plus f2 minus t by mu. Here f1 and f2, as we know, the focal lengths of lens 1 and 2. If we are going to consider this medium is vacuum, so mu refractive index value will be 1, and this expression will be f1 f2 by f1 plus f2 minus t. That means this is the equivalent focal length of two lenses separated by a distance t in a vacuum, that we know in our plus 2 level. If we are going to write in this way, 1 by equivalent focal length, 1 by equivalent focal length, this expression can be written as like this: 1 by f1 plus 1 by f2 minus t by f1 into f2. Same, this one, this expression same. Here f equivalent written, here 1 by f equivalent. Okay, 1 by f equivalent can be written like this. Now you just compare c value. Where is the c value? This is c value and this equivalent value. Here by comparing this one 1 by f equivalent and c value, we can found c equal to minus 1 by f equivalent. Here you can see this is minus f1 by f1 minus 1 by f2 plus t by f1 f2. Here this is 1 by f1 plus 1 by f2 minus t by f1 f2. So by comparing this and this c with 1 by f equivalent, we can get c equal to minus 1 by f equivalent, or f equivalent focal length is equal to minus 1 by c. You just remember, this is most important expression, you just remember. Okay. Now here we we found the system of matrix of this combination of two thin lenses is this one. In general, the system of matrix of any optical system A, B, C, D. If I am going to compare with these two matrices, we found A value, B value, C value is this one, or we can write C equal to minus of this one, D value is this one. To find the cardinal points, or to find the location of cardinal points, we should remember these expressions. Here 5 and 14 already we discussed in our previous video. Previous video, you just check lecture number 10 video, you just check. You should watch how this expression came. Okay, these two expressions x1 x2 represents what? First and second focal points from input and output planes. R1 R2 represents first and second principal points from input and output planes. And equation number 20 and 22 represents what? Location of nodal points from input and output planes. These two expressions 10 and 15 represents the first and second focal points from principal points. Location of first and second principal points. Location of first and second focal points. Okay, so we should remember these expressions to finding the location of cardinal points of any optical system. How? Here we are going to consider a numerical which is based upon this topic. Okay, here in this topic we discussed combination of two thin lenses. Here same question given that consider two thin lenses here of same materials having focal lengths 10 and 5 centimeter respectively, separated by a distance 6 centimeter. Find the location of cardinal points. Most important question. If this question will be asked in your exam, it will ask for 3 to 4 marks. Here I detail discussed. Carefully watch and make the note for your exam. What are the given? In your question it is given that f1, this is f1 first focal length, that means this lens. For lens 1 focal length is your 10 centimeter. For second lens focal length is your f2 equal to 5 centimeter. Let I have to correct it first. So here in question it is given that focal length of lens 1 is your 10 centimeter, lens 2 is your 5 centimeter, separated by a distance 6 centimeter. So to finding the cardinal points, we should know the values of A, B, C and D. because by using A, B, C, D, we can evaluate the location of cardinal points. Okay, so first we have to evaluate A, B, C, D for this case, for this combination of two lenses. For the combination of two lenses, what we found, A is nothing but 1 minus T by F1, B is your T, C is this much, minus 1 by F1 minus 1 by F2 plus T by F1 F2, D is this one. So by substituting these values T, F1, F2, here we have to first determine A, B, C, D value. So A is nothing but 1 minus T by F1. Just substitute the values. T value is your 6, F1 is your 10. Okay, so here we found this value is your 0.4. You just calculate with your calculator. B value, it is given that T, direct T here, B equal to T. So T given that 6 centimeter, 6 centimeter. Here it is unitless because this is 6 centimeter, centimeter got cancelled. So 1 minus 6 by 10, we can get 0.4. Okay, then we are going to calculate C value. C value is nothing but minus 1 by F1 minus 1 by F2 plus T by F1 F2. Just substitute the values and we can found that C value equal to this much, minus 0.18. D value is your 1 minus T by F2. By substituting T and F2 value, we can find the value. D value is your minus 0.2. Now we are going to find out first and second focal points from input and output planes. So first focal point from input plane, how we are going to determine? By considering this expression, x1 equal to D by C. So here D value is this one and C value is this one. Just substitute. We can get x1 value is your 1.11 centimeter. Okay, and this value, this is represents the focal points from input plane. Okay, so as here you just remember one thing, as this value came as positive 1.11 centimeter, that means for this case first focal point will be located towards right of this input plane. You just remember, towards right of this input plane, somewhere here like this. F1 will be here. How much distance we have to move? 1.11 centimeter. Okay, then x2 value is your minus of A by C. So here minus is there, minus A value is your 0.4 plus 0.4, C value is your minus 0.18. You just substitute these values, you can found the value 2.22 centimeter. That means from output plane we have to move towards right. Towards right, how much centimeter? 2.22 centimeter. We can get the second focal point, location of second focal point. Now we are going to find out the first and second principal points from input and output plane. So as per the expression, this one 16 and 17 equation, that is your r1 equal to d minus 1 by c, r2 equal to 1 minus a by c. So here we have to substitute d value. D value is how much? Minus 0.2 minus 1 by c, this one minus 0.18. You just calculate, you can found the value 6.66 centimeter. And r2, you just substitute the value. A value is how much? 0.4 and c value minus 0.18. You can found the value minus 3.33 centimeter. That means r1 is positive. From input plane we have to move how much distance? We have to move 6.66 centimeter towards right, then we can found the principal point. Okay, and here it is negative value. Negative value means we have to move left side from the output plane. How much distance? Minus 3.33 centimeter. Then we can found the second principal point. Now we are going to move to determine the nodal points. Here nodal points, to find the nodal points we have to follow these equations. D minus 1 by c, 1 minus a by c, both are equal with these equations 16 and 17. That means z1 will coincide with r1, z2 will be equal to r2. Okay, so here z1 and z2 value also same. So here what we found? We found that the location of first and second nodal points are coincided with first and second principal points. Now we have to find out this value, location of focal point from first principal and second principal plane. So from the first principal plane, this one, f1 equal to 1 by c. So if I'm going to calculate 1 by c here, 1 by c, that means c is your minus 0.18. Minus 0.18 means here 1 by minus 0.18 means f1 we can found minus 5.55. That means what? We have to move from first principal plane to left 5.55 centimeter left, left from the first principal plane. Then we can found the first focal point. f2 value is nothing but minus 1 by c. Minus 1 by c means same, but it is positive. That means we have to move from second principal plane towards right. How much distance? 5.55 centimeter. Then we can get the second focal point, right? Here equivalent, here c is nothing but equivalent 1 by f equivalent. So here f equivalent is nothing but minus 1 by c. Okay, so f equivalent minus 1 by c means this one. The f2 value is nothing but your f equivalent. Just remember, this is most important. F equivalent is nothing but your f2 value. F2 value means focal point which is in the output output side. Okay, output side, or you just consider the second focal point is nothing but the equivalent focal length of the optical system. Keep this in your mind, it is most important. Okay. Now we are going to validate the length between first principal point and first focal point, second principal point and second focal point. That means this length in this figure, this is the focal point, this is the principal point, this is the length, the so-called f1. This f1 magnitude is this one, and here in this figure this one f2. Okay, now we are going to validate, is it true or not? If I'm going to follow this figure particularly, this f1 magnitude is nothing but r1 magnitude and x1 magnitude plus x1 magnitude. Here f2 magnitude is nothing but f2 magnitude is nothing but x2 magnitude plus r2 magnitude. Now here in this particular question, what we found x1 value is your 1.11 plus. That means this x1 is somewhere present right to the input plane. Here somewhere x1 is present, x1, this one. That means the so-called focal point, first focal point will be here from the input plane. That means this length is your x1, right? This length is your x1 and this point is your f1. Okay, according to this question. And here r1 we found what? R1 we found plus. That means R1 is the positive. From input plane we have to move, this R1 is positive, here is 6.66. now we have to find out this distance. Okay, what is the distance between first focal point and first principal point? This point, how we are going to determine? We can determine the magnitude of R1 minus magnitude of x1. Here magnitude of R1 minus magnitude of x1. R1 magnitude is how much we found? 6.66, this one, and x1 magnitude we found 1.11. so R1 magnitude minus x1 magnitude we found 5.55 centimeter. Now we are going to find out for second focal point. Here is the second focal point, this is the second principal point. So this distance is your second focal length, this side, right side. So here we found x2 is your negative, right? x2 is positive. X2 positive means in this figure, here from output plane, this distance x2, right? Here R2, how much we found? R2 we found negative minus 33. That means P2 is present left to the output plane. That means this length is nothing but x2 magnitude plus R2 magnitude. X2 magnitude is your 2.22 plus R2 magnitude is your 3.33. If I'm going to add together, we can find the same answer, this one and this one. So whatever we have been calculated, it is correct. So you should not bother about that how the first focal point will be come over here. No, For a particular optical system like this, the focal point can be in bit from the input plane towards right. Okay. Now we are going to validate another important information. We know the system matrix of any optical system will be acceptable if the determinant value will be 1. So here a b c d values are 0.46, this one c value, this is d value. Just substitute and take the determinant. Here. This is your minus 0.4 minus 0.2 minus 0.08, and here 6 into 0.18. This is minus, so this will be plus 1.08, and we can found 1. The value will be 1. The determinant will be 1. So here also we validated the system of matrix. Okay. Here I forgot to write one thing. See, c value we found minus 0.118. It's reciprocal. Here. Its reciprocal of c is given the length, unit of length. So obviously here c is nothing but centimeter inverse. You just write. Okay. You just write in your note. Here c unit will be centimeter inverse. Okay. So here I am going to stop this class. In our next class, we are going to discuss finding the thin lens formula by using system of matrix. Thank you so much for watching this video. Thank you.